Hi, my name is Demi, and I'm a PhD student at MIT's Digital Structures Research Group with Professor Caitlin Mueller. I'm excited to share our work with you today on flow-informed topology design. One tradition in the teaching of structural design to architecture students at MIT is to encourage students to develop an intuition of designing with force flow. Force flow can mean different things in different design situations. For example, for a solid beam loaded in plane, force flow might be represented by the underlying field of principal stress. This textbook by Allen and Zalewski points out the similarity between the more materially efficient topologies, or trusses, with the principal stress field of the solid beam. Flow-informed topology design has been applied to other design problems in practice, such as ribbed floor slabs informed by principal bending moment and grid shell topologies informed by membrane principal stress. Recently, many effective computational techniques have been developed to automate and replace this intuition of force flow. However, an alternative pedagogical perspective prioritizes intuition over these types of generative methods. There are two main objectives of this research. First is to develop a tool to help students follow this principle of designing topologies with force flow, which we noticed was absent in the classroom. Second is to test the effectiveness of this tool in guiding designers towards materially efficient designs. Achieving these objectives would have several areas of potential impact. This design tool could complement finite element analysis in the classroom or in practice, especially when it is computationally expensive to use iteratively. It can also promote open-ended design over automated computational processes, which in turn helps students build intuition around force flow in a way that FEA cannot. More practically, it enables evaluating the performance of a design in progress, which is impossible for unstable structures in FEA. We developed a heuristic that quantifies a topology's conformity with an underlying vector field. We briefly show its calculation here through the example of a simply supported beam truss under midpoint load. The proposed heuristic requires an initial run of FEA to create the cross field of force flow. For a given topology, each mesh element is examined for its principal stress vectors and for nearby segments of topology bars. A nearby bar segment that is well aligned with the mesh element's principal stress vectors will contribute more to the mesh element's conformity score. These contributions are summed to produce the conformity score of the examined mesh element. Finally, the conformity of the overall topology can be summarized as the average conformity of all mesh elements. Color-coding the underlying cross field helps indicate areas of high and low conformity across the topology design. Here, dark purple indicates low conformity, while bright yellow indicates high conformity. This heuristic and visualization can be used as an interactive design and learning tool. An example exploratory design process is shown here. The user can add and delete bars while receiving feedback about the conformity of the design in progress, without requiring stability. The final design with the highest conformity may not be optimal, but it is a user-steered design that might not be generated by other computational techniques. Footage of designing with the heuristic is shown here. The user can toggle between different topologies to make direct comparisons, or directly edit a topology to get instant updates to the conformity score. It is important to check how well the conformity heuristic corresponds to material efficiency. We do this using example design problems. For each design example, we parametrically generate a series of topology options and record two values, their conformity and strain energy, where all topologies in a given example are assigned the same cross-section. These two values are plotted for each design. If the heuristic is an effective indicator of structural efficiency, we would expect a negative correlation between conformity and strain energy, with the best performing topologies in the top left corner. Results for the two-panel X-braced cantilever are shown here. For this design example, there is a strong correlation between the conformity of a design and its structural efficiency. The beam truss under midpoint load also shows a general negative correlation. This study includes trusses of varying topologies, numbers of panels, and panel spacing. A few specially designed topologies, such as the Mitchell truss and the funicular solution, are also included, corresponding with the highest and lowest performance respectively. Next, we consider floor rib topologies against the principal bending moment of a floor slab. Generally, the expected negative correlation is observed. However, there is some spread indicating that the correlation is not so straightforward. Some high-conforming topologies do not have improved structural efficiency. Examining some deviations in these plots can reveal shortcomings of the conformity heuristic. For example, it can disproportionately reward zero-force members. In this example, the addition of zero-force members increases the conformity heuristic when in reality the truss's strain energy is unchanged. One of the more complex design examples studied was for the grid shell topologies. The results show an overall negative correlation, though it is nonlinear. At the very least, the heuristic can usually predict the best and worst topology for these grid shells. These two plots show each of strain energy and conformity as a function of total bar length for the same set of grid shell designs. Both metrics identify topology A as the worst topology and topology G as the best topology for almost all bar lengths. We finish with some closing remarks on the findings and contributions of this project. Our first objective was to develop a tool to measure and facilitate flow-informed topology design, which we achieved by developing a heuristic to quantify how well a topology conforms with an underlying vector field. We also used design examples to understand how effective the conformity score would be in guiding students towards structurally efficient designs. The areas of potential impact mentioned earlier were largely achieved, with new insights on the limitations of designing with a conformity heuristic. Most importantly, designing topologies to conform with force flow has been shown to be a necessary but not sufficient condition for topology design, meaning it can augment but not replace other engineering principles like connectivity, stability, and zero-force members. Thank you for your attention. We invite you to read our conference paper for more details on this work and reach out anytime if you have any further questions.